So some important facts about the periodic table. First one is that Mendeleev was the first to develop a periodic table. He did so based off from mass, but what it was really important about this was that he actually left spaces that predicted the existence and properties of elements that have yet to be discovered. In the periodic table, we know that rows are called periods. We know that columns are called groups or families. Elements are placed in an increasing atomic number, which we know atomic number is the number of protons, and we know that elements in a group have similar properties due to the fact that each has the same number of, in this case, valence electrons. We know that our valence electrons are what give us our chemical or special chemical characteristic. The table can also be split into three groups. We have our metals on the left-hand side, our semi-metals, and our non-metals. So metals can be on the left, and when I say left-hand side, I mean left-hand side of what we call the wall or the split. We have our non-metals, which we know are on the right-hand side of the wall, and we have our semi-metals, which are touching the wall. And there are some specifics. So when we look at this, we look at our metals. Some characteristics that we know metals have is that we know that they are conductors of electricity. We know that they lose electrons. Okay, so since they lose electrons there, we know that they become positive ions. We know that they can be malleable. We know that they can be ductile. And we know that they have a high melting point and boiling point due to some of their characteristics. So since they lose an ion, just to kind of clean that up, we know that they form positive ions. Okay, our non-metals here, so if we're looking at our non-metals, we know non-metals are poor conductors. We know that they can be brittle. We know that they gain electrons. So since they gain electrons, they become negative ions. And we know that they have a relatively low melting point and boiling point. Okay, last part here is when we look at the semi-metals. So again, here's the wall. So left of the wall we know is the metals. Right of the wall we know is our non-metals. And we know some of those that are sitting on the wall are what are called our semi-metals. So we have D, Si, Ge, As, Sb, Te, and At. And these can all be found on this piece right here on the wall. A big thing to remember is that hydrogen has qualities like that of metals in the alkali metals, but is considered a non-metal. So the big key idea here is that the octet rule states that elements want to have oct, meaning 8 valence electrons, and metals tend to lose electrons, and non-metals tend to gain electrons to accomplish this. I like to think about the periodic table as being a cylinder that everybody wants to get to our group 18 here, our noble gases, and in order to get to the noble gases, you either go back around or you go forward. Okay, so again, either gaining or losing, losing being a metal, gaining being a non-metal, to achieve that full octet. So when we look at this, looking at the periodic table, since it's arranged based off from our number of protons or our atomic number, there are also some characteristics that present themselves in the periodic table. When we look at this, the first one we're going to talk about is atomic radius. Atomic radius, remember, is the distance from the nucleus to the outermost electrons. So how far out from the radius to that outermost electron is your atom. Next thing is metallic characteristics, so how easily an atom loses an electron. We have electronegativity, which is your attraction or affinity for electrons. And we have our ionization energy, which is the energy required to remove an electron. So atomic radius, as you go from left to right, we actually have a decrease. We know that because of our Coulombic forces of attraction. And as you go down, we actually are increasing in our atomic radius there. So we have an increase. When we look at our electronegativity and our ionization energy, as you go from left to right, there's actually an increase. And as you go down in group, we have a decrease in your electronegativity and your ionization energy. We know this, again, a lot of this is dealing with Coulombic forces of attraction. So the more protons we have, we know the stronger our force of attraction. Therefore, as I move from left to right across the period, I gain more protons, thus bringing in my outermost electrons, decreasing my atomic radius. Atomic radius, we know, increases as you go down a group because we are gaining more principal energy levels, thus spreading out our electrons even farther. Electronegativity, as you move from left to right, we know it's increasing. We're increasing electronegativity because of that force relative to size is causing an increase. Therefore, I can gain electrons most easily. The one element with the highest electronegativity we know is going to be that fluorine. If you look at table S, has a value of 4.0. Ionization energy goes hand in hand with electronegativity because ionization energy, remember, is the energy required to remove an electron. So if I'm gaining electrons, I have a strong attraction for electrons. Therefore, I'm not going to want to lose my electrons very easily and become an ion. So when we're looking at this, we know that positive ions, when you become a positive ion, which is typically that of our metals, we know that we have a smaller radius because we lost some electrons. Our negative ions, we know, are actually going to get larger because they gained an electron. Increases the repulsion forces between those electrons, therefore causing you to get larger. Since you've lost an electron, typically in a metal you'll lose the electrons of your outermost ring, therefore decreasing you by a whole principal energy level. So when we're looking at some of these examples, it says which of the following would have the high melting point and be fairly malleable. High melting points we know are characteristics that of a metal, and being fairly malleable would also be a characteristic of a metal. So to break this question down, really what we're looking at here is which of the following is a more metal, so farther to the left and possibly down. So when we're looking at these possible choices, we know that bromine is not a metal, we know boron is not a metal. As you're looking, we know that Be is in fact going to be a metal. So we know that this is going to be our correct response. Which of the following is considered a metalloid? So metalloids, remember, are the same as a semi-metal, so they're found on the staircase or the wall. We know aluminum is actually considered to be a metal. PO, we know, is actually considered a metal. Carbon, we know, is definitely non-metal. Therefore, we know that Si is, in fact, our metalloid. Which of the halogens would have the highest electron affinity, so highest electronegativity? Talked about this a little bit earlier, but using table S, you can actually find the numerical values of these, or you could use your trends. So if we're using our trends, we know electronegativity increases as you go up and to the right. So which of these is the highest up and to the right? We know is going to be that of fluorine. Last one here, which atom has an ion with a smaller atomic radius than the parent atom? So looking at our ions, we know that positive ions become smaller in radii. So our radius is becoming smaller. So we're looking at which of these is a metal. So if we're looking at which of these is a metal, we know that calcium is in fact a metal, while the other are non-metals, and or possibly we know that Sb is our semi-metal. So we know in this case it's going to be our calcium. Good test taking strategy for dealing with these types of questions, if you find yourself in a jam, is look at which of these are not like the others, and it'll present yourself with a pretty obvious answer, or put yourself in a fairly beneficial area to get the correct response. So when we're looking at the following periodic table, we know that each group shares the same number of valence electrons. Since they share the same number of valence electrons, they show similar chemical properties. So the first one we have are our alkali metals, which form +1 ions. Second group here we have our alkaline earth metals, which form +2 ions. When we look at 3 through 12 here, we have what we call our transition metals. Transition metals, remember, in solution make very colorful solutions. We know that they can create varied ions. There are multiple charges, and we could just call them the transition metals. So 3 through 12 gets a little unique in that, and transition metals are fairly stable, actually very stable, when we look at those as well. So as we move across the periodic table, we have our halogens, which is group 17. We know that these are very reactive. They're actually very reactive with that of the alkali metals, because alkali likes to lose an electron, halogens like to gain an electron, which makes a nice pairing. And we have our noble gases, which have their full octet, and they're very non-reactive because of that. Also, we have our lanthanide series and our actinide series. I like to remember this because the first box here is LA, lanthanide, actinide, for those series. Okay, and they're very unique with the actinides being primarily synthetic elements there. Last part here we have our phases. Okay, when we're looking at the periodic table, we have a couple different phases. We have our gas, liquids, our diatomics, and our semi-metals. Okay, so when we're looking at gases, our big gases that we have are all of our noble gases, so everything that is found in group 18. We also have hydrogen, nitrogen, oxygen, and fluorine, and chlorine. When we're looking at liquids, we really only have two liquids. We have that of mercury and bromine. Diatomic, so the diatomic 7, so some people remember it from Hofbrinkel. So we have H, O, F, B, R, I, N, C, and L. Those are your diatomics, which appear in nature in tubes. Last part we have here again are our semi-metals. So we have B, S, I, G, E, A, S, S, B, T, E, and A, T. 1, 2, 3, 4, 5, 6, 7 of those on the wall. So when we're looking at the following, we're going to be drawing Lewis dot diagrams. Remember, Lewis dot diagrams are used to show the valence electrons inside of an atom or compound. So the first one we have here is Na, so we know that we have Na. Okay, and in this case, since we have our Na, we know that Na, since it is group 1, has 1 valence electron. An ion for Na, though, we know on the other hand, we know that Na ion, since it is a metal, we know it's going to form a positive ion, so we know where we're going to have our Na here. And since it's a positive ion, we know it's going to lose that 1 valence electron, just becoming Na+. Remember, with our ions, we want to make sure that we put our brackets around those so that we know that it is indeed an ion. So when we look at chlorine, chlorine here we know is Cl. We know chlorine is a nonmetal, so we know nonmetals typically form negative ions. So chlorine we know has 17 valence electrons because it is a halogen. So 1, 2, 3, 4, 5, 6, 7. But the chlorine ion we know is going to actually end up picking up an extra valence electron. So we know we're going to have chlorine here. And we're going to end up with 8 valence electrons. 2, 3, 4, 5, 6, 7, 8. And since we picked up that extra valence electron, we know this is now going to become a negative ion. Looking at compounds here, okay, when we're looking at compounds, we have H2O. H2O is one that I told you to memorize. So H we know has 1 valence electron. We're going to know that H shares this with the oxygen here. So we have our oxygen over here, and we know that this oxygen actually ends up sharing another valence electron with this hydrogen. And we know that there's a double lone pair giving it its bench structure on the central atom. Looking at the next one, we have K2O. We know this is actually on an ionic compound. We know that K has a positive charge. We know that that positive charge is giving away an electron, and we have 2 of those, so we know that we're giving away 2 electrons here. So we know that we're going to actually have 2 Ks with a positive charge, and we know that we're going to have oxygen, and we know that that oxygen is going to pick up those 2 electrons, causing it to become a negative 2 charge. And we have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons around that oxygen. N2, one of the trickier diatomics, we know nitrogen has that of 5 valence electrons, so we have 1, 2, 3, 4, 5 to share with the other nitrogen, which is indeed going to have 2 other lone pairs. So 2, 4, 6, 8, 2, 4, 6, 8, and everybody's happy there. Carbon dioxide, another one that I told you to memorize. Carbon we know has 4 valence electrons, making it very nice to be the central atom here.
with 2 oxygens on each side. We know that oxygens want 2 valence electrons. So by sharing with the carbon here, we know that we're going to end up with a linear molecule and adding the missing pieces. So I already have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Fluorine, since it's a halogen, we know it's going to be a single bond to the other fluorine here. So we're going to have fluorine bonded with fluorine, sharing that 1. So there's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Everybody's happy there. Last one here we know is ionically bonded, so we have MgCl2. Mg we know is in group 2, so we know it's going to actually become a positive 2 ion. So Mg giving up those 2 electrons. So Mg is going to give up those 2 electrons. Oops. Those 2 electrons here, causing this to be a positive 2 or a 2 plus. And we have our chlorine, but we have 2 chlorines, so we're going to use our coefficient of 2 out in front. So we have 2 of these chlorines, which are both picking up an electron, thus giving us a negative charge on there, and show the electrons 1, 2, 3, 4, 5, 6, 7, 8, 8. There. So when we're looking at these types of things, we want to take a look into some of the key ideas. So big key idea here is atoms, they want that full octet. That's what we're looking for here, of valence electrons. Their bonding behavior is based off from their tendency and their reason. They will lose, gain if they're ionic, or even share electrons if they're covalent, is all because of that octet. That's what causes this bonding sensation to take place. So ionic bonds, we know, are the transfer of electrons. Okay, and they're typically, and these are going to actually be between a metal and a non-metal. We know that they have a high boiling point and melting point. We know that they conduct electricity in their aqueous state. And we name these we know that we name the ion both separate, and on the second we use the IDE ending. Remember, if there's multiple charges, so for our transition metals, we use Roman numerals to identify the possible charge for the cation, if multiples are possible. Remember, to neutralize compounds, we use the crisscross method. To neutralize those compounds. So when we crisscross, we take the charge of the cat, make that the quantity of the anion, and we take the charge of the anion and make that the quantity of the cation there. When we're looking at covalent bonding, okay, when we're talking about covalent bonding, we know that we're sharing electrons. We know that this is between 2 nonmetals. We know that they have a low melting point and boiling point. We know that they're non-conductors. And we add prefixes to tell the number of each of those molecules involved. So we use things like mono, we use things like di or tri, okay, telling us our different pieces. Network covalent bonds that we talked about those. We know that atoms are all linked together. And since they're all linked together, we know that they have high melting points. But we know since they are covalent, they are non-conductors. Due to their complex shape, we know that that's what gives them their abilities to have that high melting point because of their shape and breaking all of those bonds. Last part we have here are allotropes. same element, different bonds. Okay, good examples of those is carbon. Okay, carbon is mostly used for an example between those. You can think of anything, any carbon-like structure like diamond compared to that of charcoal. Charcoal you can catch on fire, diamonds hopefully you cannot. Again, showing you allotrope, same element but different compound or different bonding. Due to the different bondings comes different properties. When we talk about metallic bonds, okay, metallic bonds, remember, are fixed, positive charged ions. Okay, therefore they create this mobile sea of electrons. Okay, alloys are a good example of this. Remember, that's a mixture of different things. So they conduct as a solid or as a liquid. Because of that, we know that they have a high melting point, and they're also malleable. And again, you can see that this is the fixed cation. These electrons kind of flow through this other the electrons flow through the cations, allowing that sea of mobile electrons to occur. So when we're looking at the following, okay, it says which of the following is created by the equal sharing of electrons. So if I'm sharing, that automatically tells me that I'm going to be covalent. So if I'm looking at these, I have two choices that are covalent. I have N2O and I have N2. I'm looking at N2O, looking at the structure of that. I know this is actually going to be a non-equal sharing, so there's going to be some type of polarity because of the difference in electronegativity. Therefore, I know that N2 must be the correct response. We know that there is an equal sharing of electrons due to no difference in electronegativity, therefore giving us our equal sharing. Naming each of the following. Remember, these first ones that we're looking at are ionic, so based off from them being ionic, we can identify them rather quickly. So we know we have, in this case, magnesium with a +2, oxygen with a -2, therefore creating magnesium oxide. Next one we have here is N2O5. Looking at N2O5, we know that this is actually going to be covalently bonded. So since this is covalently bonded, I need to identify the amounts. I have 2 nitrogens, so I know it's dinitrogen. And then I have 5 oxygens, so pentaoxide. Next one here, I know I actually have something that is covalent or ionically bonded, but has multiple charges because iron is a transition metal. Therefore, I know I'm going to actually have iron 3, identifying the charge of that ion, the cation, oxide. How did I know it's iron 3? Uncrisscross, so I take the quantity of my oxygen and make that the charge of my iron, therefore giving me iron 3 oxide. 2 goes back to oxygen, which we know the only possible charge there as an anion is a 2- charge. Looking at the next one, I have actually, it looks like a polyatomic here, so I know that this is going to be silver, and then looking at table E, I know this is actually a phosphate. Okay, I know the charge of that is going to offset those, so I don't need to identify the silver charge because there's only one charge possible in order to have it bond to that phosphate. PbO2, I'm going to have lead, and then uncrisscross, so based off of uncrisscrossing, I know this is going to be lead, in this case 3. And then I know this is going to be oxide. Actually, sorry, I apologize. That's not going to be lead 3. It's going to actually be lead 4 oxide in that case, because we know this is going to be 2 times 2, which is 4. We only have one of those, so to offset that, we know that that's going to be a +4. And then this last one I have here is nitrogen monoxide. Again, because it's covalent, so I need to identify the quantities. It's not necessary to call it mononitrogen. You can just leave off the mono, leaving it as nitrogen monoxide. So writing the formula for each of the following, I have calcium fluoride, so I know that's going to be Ca. Ca has a +2 charge, fluorine has a -1, therefore I know I'm going to actually have to have 2 of those fluorines. That should be a subscript there. Okay, next I have cobalt 2 nitrate. So cobalt I know is CO, and I know I have a nitrate, so an NO3. And since cobalt is a positive 2, nitrate we know is a negative 1, so I must have 2 nitrates there. Lithium acetate. Acetate looks kind of complex, so I know it's coming from table E. So I have lithium Li, and with my lithium I have an acetate. Charge of an acetate is a 1 minus, which cancels out that 1 plus from my lithium. So I have C2H3O2 as my acetate there, and I put that in parentheses to show you the anion. Silicon dioxide, so if I have silicon dioxide, I know that's just going to be SiO2. Mono because it's nothing there it's written, so I know it's just 1. Di meaning 2, so 2 oxygens. Zinc hydroxide, so zinc I know I have Zn, hydroxide I know is an OH. Zinc I know is the only possible charge is a 2 plus, therefore I know I must have 2 hydroxides because that's a negative 1 charge. Carbon tetrafluoride, I know I'm going to have carbon, and then tetrafluoride, tetra meaning 4, so I know I'm going to actually have 4 of those. So as I answer that question, I know I'm going to have CF4. And that does it for day 3 notes.